Physics lecture number 11, Projectiles Launched at an Angle, part 1. When a projectile is launched at an angle, it initially moves diagonally. Thus, it's moving both vertically and horizontally. If we know the initial diagonal velocity v, we can find the horizontal velocity vx and the initial vertical velocity vy. And we can also find the horizontal distance delta x and the vertical distance delta y. So here's an object being launched diagonally. V is the diagonal velocity, Vy is the initial vertical velocity, and Vx is the horizontal velocity. And we can find Vy through Vy equals V sine theta. And we can find Vx by using V cosine of theta. Delta x is the horizontal distance traveled after a certain amount of time. Delta y is the vertical distance traveled after a certain amount of time. So let's go ahead and solve the problem. A soccer ball is kicked and moves at an angle of 35 degrees with the horizontal at an initial velocity of 6.4 meters per second. Find the initial horizontal and vertical velocities. Find the horizontal and vertical distances covered after 0.4 seconds. So here's what's given. The initial diagonal velocity of 6.4. So this is going to be 6.4. The angle is 35. And we don't know the horizontal velocity and we don't know the vertical velocity. So let's go about solving for that. Okay, so Vx is going to be V cosine theta. Initial diagonal velocity is given as 6.4 and it's being launched at an angle of 35. So 6.4 cosine 35. Cosine 35, 0.8192, and then 6.4 times this number gives us 5.24, which is rounded to 5.2 meters per second. So this is the initial horizontal velocity. Let's find the vertical velocity, the initial vertical velocity. Vy equals V sine theta. Vy is 6.4. Sine of theta, 35 degrees. Sine of 35 is 0.5736. The product of these two numbers is 3.67 or 3.7 meters per second. So the initial rate at which it's going up is 3.7 meters per second. So this is 3.7, and then Vx is 5.2. So we're going to use these two values now to solve for delta x and delta y. Now, the horizontal velocity, Vx, stays constant. So when the object is moving through the air like this, the rate at which it's going horizontally, that stays constant. However, the vertical velocity, Vy, changes over time due to the influence of gravity. And gravity accelerates an object downward at 9.8 meters per second squared. And we'll use negative 9.81 meters per second squared. Notice that this is a negative number. Remember that we use a negative value for acceleration when an object slows down and or changes direction. An object launched at an angle will go up, slow its ascent, reach a peak, then change direction and move down. So this object, it's going up, 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 slows down, slows down, slows down, stops, at least it stops going up vertically. It's still moving at the same rate horizontally, but the rate at which it's going up slows down, stops, then changes direction and comes back down. So vertically, it goes up and slows down, stops, and changes direction. Vertically. Alright, so to find the horizontal and vertical distance covered, we'll use delta x equals vxt and delta y equals vyt plus 1/2 at squared. Delta x equals vxt is really just the velocity formula rearranged. Velocity is distance divided by time. Solving for x, you get delta x equals vxt. So delta x equals vx, which we found was 5.2. Time is 0.4. So traveling at this velocity horizontally over this period of time, it will cover about 2.1 meters horizontally. All right? So that's the horizontal distance covered during this time period when it's traveling at that rate horizontally. Let's find the vertical change. Delta y equals VY2 plus 1/2 AT squared. Delta y is 3.7. That's what we solved for previously, over a time period of 0.4, 1/2 a, and then the acceleration is negative 9.81, and then the time is 0.4. So if you solve for all this, the vertical change is 0.7. So vertical change is going to be 0.7, and then the horizontal change is about 2.1. So what all this means is that if it's launched at an initial speed of 6.4 at this angle, after 0.4 seconds it will have covered 2.1 meters horizontally and 0.7 meters vertically. If a projectile fired at an angle lands at the same height from which it was launched, we can use the range formula to find the horizontal distance r. Knowing r, we can calculate the time the projectile is airborne and the maximum height reached by the object. So here's a picture of a projectile which, after being launched, lands at the same height from which it was launched. All right, so if the trajectory is just a straight, even parabola, we can use the range formula. But we can only use this when it lands at the same height from which it was launched. So r, and r is just delta x. We use r because it's a special type of delta x. It's the maximum horizontal range it can cover if it's launched at that angle. All right, so the range, or delta x, is v squared sine 2 theta over g, and then gravity is going to be 9.81. So let's try a problem. The cannonball is shot at an angle of 52 degrees with the horizontal. It leaves at a velocity of 33 meters per second. Find the horizontal distance it travels, find the time it's in the air, and the maximum height it reaches. So in this problem, it's shot at an angle of 52 degrees. Okay, so this is going to be 52. And then leaves at a velocity of 33. Yeah, so this is 33. We want to find the horizontal distance it travels. We're going to solve for the range right here. And then we also want to know the maximum height. All right, so how high does it go? So before we use the range formula, we're going to solve for Vx and Vy and then use these values later on. So Vx is v cosine theta, so 33, and then the cosine of 52, and that'll give us 20.32. So this is 20.32. Now we want to find the initial vertical velocity. Vy is v sine theta. Vy is 33 sine 52. So that's going to be 26. All right, so 52 degrees, take the sine of 52 times 33, gives you that. So this is the initial rate at which it's going up. So we're going to set these numbers aside, but we're going to use these later. So just sort of make a mental note of those two values. All right, so let's use the range formula to find the maximum horizontal range right here. V squared was given as, or V is given as 33, sine of 52 degrees, and then 2 times 52 is 104. Sine of 104 gives me 1089, and then if you take the sine of 104, you get 0.9702. 1089 times 0.9702 divided by 9.81 gives us 107.7, or 1.1 times 10 to the 2 meters. That's rounded to 2 significant digits. So the cannonball travels a horizontal distance of 107.7 meters. So in our problem, we've got 107.7 meters. It's about 1.1 times 10 to the 2 meters. All right, so that's the answer to the first part. Now we want to do is we want to find the maximum height it reaches. All right. Oh, we also want to find the time it's airborne. I'm sorry. So we can use Vx equals delta x over t to find the time it's airborne. So horizontal velocity is horizontal distance divided by time. Remember, the horizontal distance is basically the range, which we just solved for. 20.32 divided by 107.7, and if you solve for t, you'll get 5.3 seconds. So it spends a total of 5.3 seconds in the air. By the way, it spends half the time going up and half the time coming down. So half of 5.3 is the time it takes to go from here to the maximum, and then half of 5.3 is the time it takes to go from the maximum all the way back down to the ground. So just FYI for your information. All right, so now let's try to find the vertical height. So when the ball reaches maximum height, its vertical velocity is 0. Thus, we can use v squared equals 2a delta y to solve for delta y. We use this formula anytime an object starts from rest or comes to a stop. In this case, vertically, it comes to a stop because it goes up, 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 slows down, stops. So since, at least in terms of vertical motion, it comes to a stop, and we can use this formula right here. So v squared equals 2a delta y, and then the rate at which it was going up vertically initially was 26, 2 times acceleration 9.8 delta y. And if you solve for delta y, or rearrange it, you'll get 26 squared over 2 times 9.81. And then solving for this, you'll get 34 meters. All right, so this turns out to be 34 meters. So what it all means is that if you launch our projectile at 52 degrees at this velocity, and if it lands at the same height from which it was launched, it'll cover a maximum range of 107.7 meters, and it'll reach a maximum height of 34 meters. And by the way, it'll reach this maximum height at 5.3 divided by 2 seconds. All right. In case you ever get a problem where they ask how long it takes to reach the maximum height, that's how you can do it. Okay. For a PDF transcript of this lecture, go to www.richardlilly.com. This has been Physics Lecture number 11, Projectiles Launched at an Angle, Part 1. In Part 2, we'll show you how to solve more difficult problems where you have to use the quadratic formula.